In this demonstration, you'll learn how to set up a simulation describing a polymer electrolyte membrane fuel cell using ANSYS Fluent in conjunction with the PEMFC add-on. At this point, I have loaded a mesh describing the fuel cell into Fluent. Now I need to enable the PEMFC add-on module. Before I can set up the simulation, I need to compute the surface area of the membrane. I'll select projected areas in the report section of the Post-Processing tab. The area of interest is equivalent to the cathode terminal surface area. This value will be used later. Now I can open the PEMFC model interface and set up the physics for this simulation. Under the Model tab, I can change the model types and relaxation factors used. For this case, I will keep the default options. Under Parameters, values describing the electrochemical and material properties may be manipulated. Again, I will keep the default parameters. Under the Anode tab, I set the anode zone types. The current collector corresponds to the anode CC zone. Here, hydrogen gas will be oxidized, generating electrons and protons, which can diffuse into the cathode portion of the cell. The flow channel describes the portion of the cathode cell that the hydrogen flows through. For this case, the porous electrode refers to the membrane through which the incoming hydrogen gas can diffuse. I can change values describing the properties of this membrane under cell zone conditions. I can control another set of values describing the anode catalyst layer as well. In this case, the anode does not contain a microporous layer. With the anode cell zones appropriately specified, I can set the zone describing the electrolyte, which is a proton exchange membrane. I will keep the default cell zone conditions for this case. Now I will set up the cathode, which of course is structurally analogous to the anode. The current collector for the cathode will collect the electrons generated by the anode cell. The flow channel will conduct a flow of oxygen to the electrode surface. The cathode's porous electrode will facilitate the diffusion of oxygen gas from the cathode flow channel. The catalyst will, of course, catalyze the conversion of the diffused protons and oxygen to water. The cathode will contain a microporous layer in this case. In the Advanced tab, I can set the contact resistivity for each electrode. In the Reports tab, I will set the projected surface area for each electrode. The cell zones describing the electrolytic cell have been specified. Now I will set up the operating and boundary conditions. At this point, I have set up the boundary conditions for this simulation. The cell will operate at a pressure of 200,000 pascals. The anode voltage terminal will operate at a constant temperature of 353.15 Kelvin. The voltage terminal will operate at a constant electrical potential of 0 volts. Similarly, the cathode voltage terminal will operate at a constant temperature of 353.15 Kelvin. The electrical potential will also be constant and set to a value of 0.65 volts. The anode gas flow inlet will operate at the following mass flow rate. The flow will travel in the direction normal to the boundary. The total temperature of the inlet boundary will be 353.15 Kelvin. Gas entering the anode inlet will be composed of hydrogen and water with the following mass fractions. The liquid saturation is set to 0. The cathode gas will enter the inlet at the same direction and temperature. The gas entering here will be composed of water and oxygen with the following mass fractions. The liquid saturation is set to 0. The anode and cathode outlets were set to have gauge pressures of 0 pascals and reverse flow temperatures of 353.15 Kelvin. Now I will run the case. To summarize the results of this simulation, I produced a number of plots. This plot describes the current flux density at a YZ plane located halfway along the length of the fuel cell. The vectors are colored according to their magnitude. At the same plane, I plotted a contour describing the capillary pressure. Note that the capillary pressure is continuous in the Y direction. To see how the mass fraction changes in the direction of the flow, I plotted a contour showing the mass fraction of hydrogen gas at a lengthwise cross-section. As you can see, the mass of hydrogen decreases in the direction of the flow on the anode side of the cell. Here's a similar plot on the same plane describing the mass fraction of oxygen. The oxygen decreases in the direction of the flow on the cathode side. This concludes this demonstration showing you how to use the PEM fuel cell model in ANSYS Fluent.